recording session.
Okay, the surprise first. Half an hour ago, I said, minding my own business, did all my talks for the day, computer's back at the hotel. I think you're on stage in half an hour giving a teaser talk. So, borrowed computer, and I'm ready to tease you. Everything is live. Every piece of code you're about to see is just about to pour out of my fingers live in front of you. So, the surprise was for me, the tease is for you. The new piece of information also is that I understand that this was going to be a very popular class, and they asked if I would do a second one. So apparently there is a second one scheduled, so you'll have a choice of 2 3-hour blocks. And so I don't know when the other one is. Almost certainly it's not in the printed brochure because we haven't discussed it until now. So you have 2 different opportunities to come. I'm guessing if you're here, you're already interested. All right. So I've taught the advanced Python segment before at PyCon in US, and we spent about 45 minutes on Unicode, and what we found is that lots of people who've been using Python for a long time thought they knew Unicode, and Unicode was a subject that if you stick your toe in the water and just learn a little bit here and there, you will always be tripping all over yourself and never be able to actually solve any real problems for it, be prepared for the issues that come up. So I take 45 minutes to just dive in head first and solve all the Unicode problems once and for all so that you walk away with a deep, profound, and true understanding of how to use Unicode in Python and are prepared to handle a wide variety of problems. You'll walk away with the problem-solution pairs. Problem, all of my text is pairing backwards. What's causing it? Problem, I take something and stick it in my database, and now I go to retrieve it, and I can't get it back. I can see it, but I can't get it back. There's a particular problem associated with that. Questions about encoding. All of these answers will be yours. Optimization seems to be a topic that people ask for over and over again, so I will give a number of optimizations that are unique to CPython, some of the simplest things that you can do to get your programs to run a little bit faster, including we'll give you a tour of the iter tools, but also some minor code change-ups that can be made to do optimization and demonstrate some profiling. And so it's kind of a core skill. It's one that also applies equally well to Jython and IronPython. I've been informed several times that almost none of these skills apply to Python, where the computer does everything for you. So if that is your tool of choice, you'll probably have no interest in the optimization section at all. Well, to me, part of advanced Python is making sure you know the basics really well. So we do a quick whirlwind tour back through all of the basics of Python, but with an eye towards mastery. And so a basic of Python is a for loop. An eye toward mastery is, I remember it had an else clause. What does that do? While loops had an else clause. Who remembers else clauses for loops? And knows exactly when they execute and when not, and what the, you guys are good. Okay, so we might go through that section rather fast. The idea is to hit the corner cases and less usual features with the idea that you will walk away with a deeper knowledge of the core language. And we'll be emphasizing Python 2.7, but talking about features that are also in Python 3.2. One of the things that's really fun to do is you've been using dictionaries for years, you've been doing object lookup, whether you know it or not, you've been using descriptors. And I've had a separate talk on descriptors that seems to be very popular. This time I'd like to approach the topic from a different angle. And so what we're going to do is just make code together and build Python from scratch, with the idea being if all you started with was under get attribute and under get item and list, could you build up the rest of Python? So we'll spend a few minutes and make ourselves a dictionary from scratch, including all the methods. What's this good for? Well, if you already know what a hash table is, the notion of a hash table won't be particularly educational. What will be educational is we will rewrite all of the dictionary methods, and so you'll walk away with a profound and deep knowledge of exactly how they work. Then we'll start with object lookup, with the idea that classes and instances are just a chain of dictionary lookups. And so we will build that chain so with the idea that if we didn't have classes, we could have built our own, and we'll build a set of functions that emulates Python's internal behavior with the idea that you can reprogram it and that it will show you some surprising things inside Python, like where descriptors get attached, how they work, and I think it'll leave you with a fairly deep understanding of Python. Who's excited about all of that? Fantastic. Now, what do we do today? I could steal all of my thunder and give you all of the slides if I had my computer and if I were willing to part with that information in advance, which I am not. So, I can take you to a couple different places. One is, I wrote a blog post recently called Python's Super Considered Super. This is a response to an old article, Python's Super Considered Harmful. I consider it to be super. Super has amazing magic superpowers, and we'll cover in the advanced class what some of those are. But I will demonstrate one of those superpowers in a moment. It's probably enough to, at this point, to make you go, whoa, I really think super is something that, there's something there that I didn't know was there. And I will show you just enough to tease you to say, it's cool, but it kind of bothers me. It just seems like something's a little bit off. What we'll do, though, in the advanced class is actually approach it from first principles and walk our way through so that it is actually a rock-solid development tool. It is not something that is misdesigned. It's not something that's actually even hard to use. There's just a set of core principles for using it, and once you know those principles, it's easy to use effectively. So this is the blog post. If you would like to do some pre-reading for the class, look up either my name or just Super Considered Super will take you right to the article. Who's read the article already? Okay. Surprisingly, not that many. The reason I'm surprised is it got over 20,000 page views in the first week. It was an amazingly popular article. Got lots of good feedback on it. Laura helped me turn it from something unreadable into something that was readable. And I had a number of, it's not just the Raymond opinion here. I had a number of Python core developers go through and do a peer review of it before it went out. So there's a lot of good information in there. So if you want to do a little pre-reading there, it's Super Considered Super. Today, you get a tease. What else can we do with the little time that we've got here today? You know what's a really fine and cool thing is bloom filters. So I wrote a bloom filter recipe. And what I like about the bloom filter recipe is it's all of 22 lines of Python, including spaces and an import and a comment. There's not a whole lot who here knows what a bloom filter is? Okay. And so what I'm going to do in our little teaser section is just tease out the idea of what one is so that you have a new piece of knowledge. So without further ado, let's start programming live. Cool. Jump on the screen. Scroll this off. Alright, so you got your random module. If you guys want to type along, this is fun to do. From random, where to start? What do we got here? We got a constructor random. And random can be instantiated with a seed. So I could tell it 1, 2, 3, 4, and on that random object, I can run the random method. Gives me a value. If I then use that same seed again, I get exactly the same value. In theory.
That's the seed in the sign.
I see how it is. Just going live. From computer, none of your own slides, none of your keystrokes work. All right. So it reproduces the same number that we've got before. So file that away. What else can you seed random with? You can seed it with a string. Rachel, that's my wife's name. Who's used the sample method before? Okay, just a couple of you. So I introduced a method into Python probably about 6 or 7 years ago for random sampling without replacement. It's actually a nice piece of code. If you want to improve your Python skills, go take a look at that piece of code. It's short. It shows an implementation of the strategy pattern. And strategy pattern is one where the module decides on its own, based on the parameters that you give it, what is the most appropriate strategy for choosing random selection. So it chooses between one or two different algorithms, and it shows you how both are implemented in just very few lines. So I want to take a sample of, let's say, sample, and I give it a population of range 60. Actually, I think the number should be like 56. And pull out 6 objects. So I have 6 numbers between 0 and 57, excluding the 57. I think 57 is right now. What's special about 57 and 6? I believe that is the number of possibilities in the California lottery. I do come to you from California, 9 time zones away. All right. So I could type something like this. Random. Let's instantiate it with my wife's name. Take a sample without replacement of range 57. And I'm back control I just now. Go to the beginning of the line, the old-fashioned way. You can take the output of such a thing and feed it to sorted. That will give me a sorted list of 6 numbers without replacement, keyed off of my wife's name. I would like to call those her lucky numbers. Buddy Mr. Hastings is also a lucky man. This is Armin. Okay, so we have 4 sets of lucky numbers. You guys know where I'm taking you already? Let's build a set. Let's start with the empty set. And let's append to that. Is Control P going to work? No, that would be too easy. And caps lock works on here. Guess who does not? My person I borrowed this from must not be an Emacs user. And update. I am going to update this set for Rachel's random numbers. No surprises so far, except that our ordering is lost. I am going to update that set with Larry's numbers. Now, did we see any overlap between Larry and Rachel?
Yeah, if you want.
Okay. Oh, that lack of an end is going to kill me. All right. Should be easy to validate that with yes. Okay, so we've got 11 numbers. There's a little bit of overlap between the two. And I'm going to add into that Armin and Laura. S, and if they were all disjoint, we would have 6 times 4 or 24 entries, but there's only 20, so there's some overlap between the two. Let's see what our set looks like. Now, this is out of all of the possibilities. Remember, there are 57 different possibilities. So, I'm going to call this group my special group. And I want to know if somebody is a member of that group. I'm going to do a hash lookup. So, let's take this, and the way I'm going to do the hash lookup is I'm going to ask this person whether their lucky numbers are the same as our lucky numbers. I'm wondering about Jacob. Okay, so there's a Jacob set. I would call that T. There's S. Now we can ask, is T and S? Until he's not in our pool of lucky numbers. So we can take the family's lucky numbers and group them all together. This is a Bloom filter. You collect the lucky numbers for all the features that you are interested in. So let's imagine a spell checker. A spell checker take a dictionary, we loop over the dictionary, and for every word in the dictionary, we compute the lucky numbers for each word in that dictionary and add it to the set. Now, we take some document that we want to spell check, and we take all of the words in there, and we take each word, and we check its lucky numbers. We compute its 6 numbers, and we check to see if they're in that set. If they're all in it, we conclude with fairly high probability that it is a correctly spelled word. If, on the other hand, it's not there, we know for certain that it is not one of the words, and so we will always identify those cases with 100% probability. And that is how spell checkers work. Now, these digits, there's a better way to store them than in a set, and we can store them in a list. So let's take an empty list. I will call it B times 57. Now, for every element in our set, what I'm going to do is mark that part of the array as being true. I'll just set it to a 1. So this is an alternative way to store our set. We're storing it as a bit array. So it's got the same information. We know that it tracks the numbers between 1 and 57 and determines whether or not they're in the set. And I can ask it questions like, is B at 3 in the set? It says no, there's nothing there. How about B at 5? And B at 6. Very simple. So that is an alternative, more space-efficient storage of the set. Let's look at the real code. This is the working code for a Bloom filter. Again, very few lines. We import random. We instantiate a byte array. So a byte array takes up 8 bits for every element. They're consecutive in memory, so it has no wasted space. Like with a list, it's just a array of pointers out into memory. Whereas the byte array actually uses the memory directly. And there's no ref counts associated with the entries. It's extremely space efficient. So we allocate the proper number of bytes. We decide the number of probes. The number of probes corresponds to the number of lucky numbers. So in my early example, each person in my group of friends had 6 lucky numbers. So get probes is a generator, or returns a generator expression, rather, that does exactly our computation of random sampling before, except this time it allows replacement because it takes too much extra computational effort to compute the replacement. So for the number of probes, we choose a random number in one of the bins, and that random number is based on the key that we're looking up. In other words, get probes is the function that computes the lucky numbers for any person. So if we type in Larry's name as the key, I would get back Larry's lucky numbers. You see the correspondence between the two? The interesting part is how we did the update. We loop over a set of keys. Let's say we're given all of the words in a dictionary. We pass those in as the keys. And for each key, we do get probes, compute its lucky numbers, and then add those to the array. The divide by 8 is, I would like to take advantage of all 8 bits in the array. So I'm using it as a bit array instead of as a byte array. And then the contains operation does exactly the reverse. We take for a given key, we find for each of the lucky numbers, we check to see if they're in the array. And we only return true if all of them are in there. So if you share all of these lucky numbers, I think with a fairly high probability, you are in the Bloom filter. So that's how Bloom filter works. Give you some thoughts on space efficiency. So I've got an example with 125,000 words in the dictionary, and we take 14 probes for each, which is 14 lucky numbers, and come back, and that gives us our Bloom filter, which we can then, the spell checker part of it is where we just take a piece of text, split it up, lowercase it, and for each word we check to see if it's in the Bloom filter. And that's all it takes to implement a very space-efficient spell checker. Question for everybody: how much more space-efficient is this if I had written it in C than Python? We know C is dramatically more efficient, right? It takes up the exact same amount of space. The byte array is the dominant component of memory here. So we have 125,000 elements. We made the bloom filter a little bit bigger than that so that there was room for some spaces in there for things that aren't in the set. So 250,000 elements, but divided by 8 because we're using 1 bit for each. So that takes us down to 30,000. So this is 30K of memory, which I think is pretty amazing for a spell check of 125,000 words. You learned something new? All right, fantastic. So one of the things we're going to do in the advanced Python class, this time with slides, this time with some exercises worked out, exercises that have answers along with them. We're going to build a dictionary from scratch. We're going to build class lookups from scratch. We're going to review all the basics of Python, but this time with the eye toward mastery of the features. We're going to talk optimizations a little bit, answer a few questions, and then we'll do something cool with Super. Would you guys like a little teaser for Super? What could possibly be done with this thing? And how long is this demo going to take? Not long. What have we got in our directory? We imported, there's in Python 2.7, there's a new class called counter. So let's say counter abra, head abra. And that will take that iterable and return back a dictionary with the counts of each letter. It's a nice, handy little routine. It has some nice methods on it, so I can ask it what are the most common letters, and it will sort it for me and say I'm interested in the 1 most common or the 3 most common. So it's a quick way of you scan all of your you scan your log files for the number of hits on web pages. You feed it into Counter, and it tells you your 10 most popular web pages. So that's kind of cool. We've got our ordered dictionary. You guys seen ordered dictionaries before? Ordered dictionary remembers the orders that keys are inserted. So here's an ordered dict. We add in A is 1 and B is 2. And how does it display? It actually remembers the order effectively as if it has stored a list of tuples inside. Of course, it's implemented much more efficiently than that, but it's effectively like a list of tuples. It remembers the orders that the keys go in, which is reasonably handy. You read in an XML file, you do a little bit of processing on it and write it back out so that it will be readable to the person who wrote it in the first place. It's kind of nice to send it back out in the same order it came in. Same thing if you're munching a JSON file or somebody's config file. It's really nice to keep the order intact even though it's conceptually a mapping. So who thinks ordered dicts are reasonably cool? Who thinks counters might be handy every now and then? So what do we have to do to get ourselves an ordered counter? You should be able to compose these things, right? Let's just make one. Class, ordered counter, subclass from counter, and ordered dict. And I'm going to have to write a whole lot of code for it. You guys ready? All right. There's a lot going on under the hood here. What is the base classes of counter? Ordered counter inherits from, or counter inherits from dict. How is it I got an ordered dict shoved in there so that counter used the ordered dict instead of itself? And the answer, the T's, has to do with super. And I will teach you how to have this kind of Jedi control over super also, so that you can do neat and wonderful things, document them well, and allow yourself to create composable classes that can be composed exactly like this. Now, in my published example of ordered counter, I have to admit I did a little bit more code than this. I gave it a custom repr and I gave it a custom reduce function. Other than that, no other method had to be added. Who thinks that's fantastic? Who'd like to learn that skill and learn how it works? It is not magical at all. It is a very controllable process. You can design that method resolution order on purpose and say, I want counter to now use ordered dict instead of dict. And you'll be able to say it explicitly with this line, knowing that you're explicitly saying insert the order dict instead of the counter. Who thinks that's fantastic? All right. Are you suitably teased? All right. Thank you very much.